Hello students, welcome back to this lecture. What we have been looking in this particular lecture is trying to understand the power across the time domain for an inverter which is actually switching. At the output side it is actually it is rising to 1 and then coming back to 0. So in this particular case, so if I pick a pointer, so in this particular case what we are saying is this is the power which is kind of consumed by the capacitor while the capacitor is getting charged from 0 to VDD. That means that the output voltage here is rising. It is going from 0 to VDD, and in this particular case the power, it is kind of the opposite of what it is consuming. So the power, it is kind of dissipating through the NMOS transistor. So it is this particular thing, we can say that the output node voltage while the capacitor is discharging, it is discharging from VDD to 0. Right, so and here this particular profile is from 0 to VDD, right? And I'm going to ignore this particular case where it is going from VDD to 0, right? So this particular portion I'm going to remove now, right? So I'm going to be interested in starting with the capacitor getting charged. So the output node voltage will go from 0 to VDD, and then while it is going back from VDD to 0, so I have a step input where it is going from the step input side, it will go from 1 to 0, and then here the step input will go from 0 to 1, right? So in that particular sense, what should be the energy that will be consumed or rather it will be stored by the capacitor? So as we know that the energy term is nothing but the integral of over time of this particular instantaneous power. So if I actually look into the energy term for this particular instantaneous power, it is actually nothing but the addition at instantaneous, the addition of all the powers, all the instantaneous powers at that particular time domain, right? So if I want to do, it's basically an integration. So starting with this particular value, so the energy that has been consumed or the energy that has been stored by the capacitor, so it will be nothing but the integral of this particular expression, and then it will be nothing but the integral of this particular expression. So across this particular time domain, I should be able to draw a particular energy profile. So when it is at this particular starting point, when it is at 0, right, so we will have the 0 value here of the energy, and while it is increasing, and in fact you will see that for this particular profile it is linear, and then it will be the integration of it will be some kind of an exponential profile and exponentially decreasing profile. So while it is kind of linear, I will have a square, with respect to linear, in the sense it is this particular power term is linearly having a linear relationship with respect to time domain. So in this particular case, when the power was linear, the energy, because it's an integral of the linear relationship with respect to time domain, so this will be a function of t square. So it's a square of the time domain. So it's going to rapidly increase over the time, over the portion where it was linear. And then we have this kind of then exponential profile and then exponentially decreasing profile. So I will have a kind of integral of the exponential profile, which will form kind of a Gaussian profile here, or close to a Gaussian profile. And while it reaches to 0 here, somewhere here, right, so the 0 addition to whatever is the accumulated energy here will have will retain that accumulated energy. So whenever the power reaches 0, we'll have a 0 the constant value here for the energy. And then it rapidly drops to here. So I will have a drop here, and then so it will be going back to 0. So I will have this energy term. So whatever is the accumulated energy, this particular power in the negative side will be able to subtract this particular accumulated energy. It will be able to subtract and then make it 0. So the time it goes to 0, we will have the 0 value here. So what this particular profile says is, while the capacitor is kind of charging, I will have the accumulated energy, I will have the energy stored in the capacitor. And while the capacitor is actually discharging, the capacitor is discharging from VDD to 0, the stored energy will be released through the NMOS transistor. So it will be released through the NMOS transistor to the ground. So this particular profile will bring back the energy that will be stored in the capacitor to 0. So before this, the energy stored by the capacitor is actually 0. After this, the energy stored by the capacitor will be 0. Right in between, while the capacitor is charging and the capacitor is discharging, I will have the energy profile with respect to time domain, and eventually it will be 0. Right, so for the charging, I will have half C VDD square, and discharging it will come back to 0. So this particular, the magnitude of this particular line, while it is completely charged, so that means while it is completely charged means the power is 0 here, because the current will be 0 after it is completely charged. I will have this particular level as half C VDD square. Okay. Now I want to compare this energy of the capacitor with respect to the energy delivered by the VDD. And if I notice the energy delivered by the VDD in terms of an expression, it is nothing but an integral expression of VDD, which is a constant multiplied by the current of the capacitor. Right. So if I go back to the previous slide, this is my the current, and if I do this particular current profile was this is negative, positive, negative, right? So if I consider the current of the capacitor in the charging direction, I will have this positive charging one, and then this negative while it is discharging, right? And if I consider this one and multiply by a constant of VDD, I will have the same profile. So the power profile of the VDD, the power delivered by the VDD with respect to time domain, will be nothing but the same profile as that of the current, right? And if I want to do an integration of that, so I need to start accumulating the points across all the time domains, from this particular point to this particular point. So if I go back to the present slide, so what I've done is I've started accumulating all the points on the, because the profile of the power of the VDD will be very, very similar, right, to that of the IVDD, or rather the capacitor, right, with respect to time domain, right? So because VDD is a constant, and constant multiplied by the profile IC of t will give me the similar profile. It will be slightly be scaled because of the VDD value. And if I do the integral of this particular the power profile, I'll get the accumulated points something like this. Right, so it will have, it will start from here, and then because of the constant value of the current, I will have a linear profile, and then we will have, I'll have an exponential profile, which will be nothing but a Gaussian profile here. Right, so the integration of the exponential profile will give me close to the Gaussian profile, and finally it will reach to a value which will be nothing but C VDD square. Because this is the energy that is being delivered by the VDD, and this particular level is half C VDD square, because this is the energy that is to be stored or consumed by the capacitor. Right, so I have written here the energy delivered by the VDD follows the Gaussian profile. Right, so what we observe here in this particular case is the energy that is kind of delivered. Right, it is delivered for by the VDD, right, one time, and this is the energy profile. And if it delivers the second time, I will have something like this. This is the second time. And similarly, if I have the, the switching of the output voltage from 0 to 1, 0 to 1, 10 times, I will have the energy delivered by the VDD will follow this particular profile 10 times. So I will have C VDD square. The second time the output switches from 0 to 1, I will have 2 C VDD square as the level. The 10th time, it is going to switch. The output node voltage is going to switch from 0 to 1. I will have the energy delivered by the VDD as 10 times the CVDD square. Right? So in short, what I'm saying is, right, if I have the profile of the energy with respect to time domain, the energy delivered by the VDD, right, I will have this particular profile and this particular profile, and it will keep on going, which will give me the value of the magnitude value C VDD square, 2 C VDD square, 3 C VDD square, 4 C VDD square, and then so on. So the number of times the output switches from 0 to 1, from 0 to 1, from 0 to 1, right, the energy will be delivered by the VDD so that the capacitor charges to VDD. so that the capacitor stores half CVDD squares, but the energy that is being delivered by the VDD rail will be nothing but 1 C VDD square, and then the next time there is a switching, it will be 2 CVDD square, 3 CVDD square, and 4 CVDD square, and so on. Right. So let's say that, in this particular statement, if the gate switches over some time interval, and then the load capacitor charges for how many times, right? Then this is very important, because just to understand what is the overall energy that is being delivered by the VDD, we need to know what is how many times the load capacitance charges, right? So let's say that the output gate switches in 1 gigahertz, right? So what I mean by 1 gigahertz is the output node switching from 0 to 1. And it happens at 1 gigahertz, right? So in that sense, if it actually switches, for every 1 gigahertz means for every 1 nanoseconds, there is a switching. The output switches for every 1 nanoseconds. And if my time of interest is for a longer duration of, say, 10 nanoseconds, right? So what it means is I have taken from 0, 1, 2, 3, and up till 10 nanoseconds, right? So all this scale are in nanoseconds. So I'm going to write it like nanoseconds. The output is actually going. So the output means I'm going to draw the output voltage, right? It switches here. And then somewhere it comes back maybe. And if it switches here, comes back here, switches here, comes back here, and then so on. It switches here and then comes back here. So from 0 to 10 nanoseconds, or maybe in the 0th second also, I'll write that it switches. And then from here till, this particular portion, it is going to switch how many number of times? So the number of transitions the output node does will be nothing but FSW multiplied by the time duration here, the time of interest we are having. Right, so over a time of interest t, and if I can calibrate or characterize the switching rate of that particular gate at the output side, I can have FSW multiplied by t. All right, so hope this is clear to everyone. So I'm going to take one more slide here. So I'm going to insert one more slide, new slide, and then say that, okay, let's say I have a clock. So I have a clock here of, let's say, 3 gigahertz, or let's say 2 gigahertz. So this clock is there for the overall chip design. And let me take one reference. So the rising edge I'm going to take. Right. So, and then I'm going to have kind of a reference so that it becomes easier for my drawing. And let's say that this is my clock frequency, F clock. And let's say that the output of that particular gate, whatever gate we have designed, it is going to switch only at, after every 2 such clock cycles. So what I meant was the switching of the gate, in this case, it could be an inverter or any kind of a combinatorial circuits. Let's say that it is going to switch, in this particular case, it is going to switch somewhere here. So the output is going from 0 to 1. So this, although it is an F clock, it is a clock signal, clock of time, and here it is nothing but the output of time, although I've written it as a frequency of gate. So it is basically the output voltage with respect to time domain. So it is going to switch from 0 to 1, and then somewhere it is going to go back, and then after this thing it is going to switch, and then somewhere here. So after every 2 clock cycles it is switching, right? And then similarly somewhere here, right? So if suppose this particular clock, so the F clock, let me say that this is 2 gigahertz, my F switching is turning out to be half of that 2 gigahertz. So I'm going to say that this is 1 gigahertz, right? So my overall energy, right, which we know, which we calibrate in terms of the frequency, I can actually establish an expression. But the switching frequency can always be a function of the clock frequency, right? So the clock is a global signal, and we know the global signal or the global clock signal's frequency. And if I can characterize almost all the gates, whatever combinatorial circuit gates we have, and it's going to switch at the output side, it is going to switch, I can have a relation with respect to that of the global clock signal. So I can have a factor, activity factor, multiplied by the f clock. Right? So with respect to the clock signal, I can have this alpha. In this case, alpha could be nothing but 0.5. But generally, we won't be having such a fast switching or the output, such a high frequency of the switching. Because if I have a very high frequency of the switching, that means that every time the energy has to be delivered by the VDD at every of this switching output. So here, if the switching output is there, I have to deliver C VDD square, and here also C VDD square, here also C VDD square, and then so on. Right? So in this particular instance, I have to actually deliver, for the overall instance from here to here, I have to deliver 4 C VDD square. Right? So, but in terms of the clock signal, I can write it as alpha clock, f clock, and where alpha is nothing but the 0.5. Right? And so using this particular expression of FSW, so FSW is nothing but the activity factor alpha and then the f clock. So this is alpha is nothing but the activity factor. So using this particular factor, we are going to establish the energy and the power expression. Right? So that's what I have rewritten here. If the gate switches FSW times over the time interval T, the load capacitance charges TFSW times. So the overall energy that has to be delivered by the VDD will be nothing but this whole component multiplied by C VDD square. So that's what I have written here. The energy that has to be delivered by the VDD, if it switches TFSW times, it will be nothing but C VDD square FSW into T. And the average power delivered by the VDD, the average, the time duration of interest is, if it is T, then I will take it as T here. So C VDD square FSW T divided by T. So this T and this T will get cancelled. So the average power delivered by the VDD turns out to be C VDD square, the output node switching frequency. So the average power delivered by the VDD is nothing but C VDD square FSW. And this is the average power VDD is nothing but the dynamic power, right? So it is the dynamic power in the sense it is nothing but the output node switching or the output node switching power, also called as the switching power or the dynamic power. And it is not called as a static power because static power is always related to a power that is being dissipated by the circuit, that has been consumed by the circuit when the output voltage will be in a steady state, right? So this particular dynamic power is used, right, for the output node while it is establishing the steady state, while it is doing the transition, right, from 0 to 1, while it is while the capacitor is actually doing the charging from 0 to 1. That is when it extracts the power from the VDD, right? So it is called as a dynamic power, and it is not the static power, and we will have a look into the static power later on. So this is the P average VDD, which is nothing but the switching power, also called as the dynamic power. And in terms of the clock frequency, we can write it as alpha f clock C VDD square, right? So the average energy over the clock, it is the average energy over the clock will now become alpha C VDD square, right? So in that sense, what I'm saying is if the overall energy, right, if the overall energy is nothing but C VDD square into FSW into T, right, so the average energy for the particular clock, we can consider it to be nothing but alpha C VDD square, right? So FSW into T will give me the number of switching, but over a clock, I can also write it as alpha C VDD square. So this will give me the average energy that will be delivered for one clock time period, for one clock cycle, right? So if suppose this FSW into T will be nothing but 10 value, so I will have to deliver 10 CVDD square, that is the energy delivered by the VDD, right? So it has to deliver 10 times, right? But for one particular clock cycle, what should be the energy delivered by the clock, and that is dependent on alpha CVDD square. Right, so that is given by alpha CVD square, where alpha is the activity factor that is that defines or characterizes the output node of the gate. Right, so this is what I have stated in the previous slide, activity factor. And activity factor is generally either it is measured and then stated, or you can also consider it to be a probability factor. So the probability that the current node does the transition from 0 to 1. Because the VDD supplies the energy only when the output changes from 0 to 1. So it is basically the activity factor. You can do two methods. One method is to characterize the output node and see how many, so see the history of it, how many times it is going from 0 to 1 for a particular design. And then while we are designing the new chip, if we are using the same subsystem or a system, we can use that same characteristics. The other way is to use the probability factor. Because the gates are also nothing but the logic designs, and based on the input combinations we can have a probabilistic method to identify how many number of times or what is the probability that the output node of the gate does the transition from 0 to 1, right? And we are only interested in 0 to 1 because that is when the VDD is going to deliver the energy or the power. All right, moving ahead. So I'm taken an example here. So this is an example. So in a 65 nanometer technology node, we know that the lambda will be 25 nanometers. F clock is given as 1 gigahertz, and generally this will be the case for a 65 nanometer technology node. A chip is designed which consists of so many of the logic gates, and then the memory also has so many of gates. So the gates used is 50 millions here, memory uses 950 millions. So total put together is I think 1000 millions. Right, so width of the transistors which were used to design the logic gates was actually 12 lambda. Activity factor for this particular logic gates on an average is for 15 to 10 raised to 6 logic gates is nothing but 0.1. So the output of all these logic gates, 15 to 10 raised to 6, the average activity factor turns out to be 0.1. One could have a slightly better, one could have a slightly lesser value. But overall on average it is considered to be 0.1. For the memory, the gates that has been used, the width is 4 lambda. Notice that the the width for the logic gate is 12 lambda here. The width for the memory is 4 lambda here. Logic gates generally we need the computational to be faster, so that's why we have used a higher width. Activity factor for the memory design is considered to be 0.02, right? So it is again an average value. So the memory, whatever the logic gates, 950 million gates are used, and an activity factor for on an average across 950 millions turns out to be 0.02. The gate capacitance and the diffusion capacitance are given for this gates, and it is 1 femtofarads per micron and 0.8 femtofarads per micron. Right. So what we are supposed to find is estimate the power dissipated by the VDD for the chip. So this is basically what we are asking is an estimate the average power across the clock cycle. So the average power by the VDD will be nothing but alpha f clock C VDD square. Right, so the energy is nothing but alpha into C VDD square for one particular clock cycle. But for if I want to find out the power, it will be nothing but f alpha f clock multiplied by C VDD square. So this f clock is nothing but 1 gigahertz, VDD is nothing but 1 volt, so that is gone. So what we will have is alpha C, and then this will be considered as a noon parameter. So this is basically noon. This is something we need to evaluate. So alpha into C, we can have the alpha parameters for the logic gates will be different, and for the memory it is different. So I am writing this as alpha LCL, the capacitance of the logic gates and activity factor for the logic gates, and alpha for the memory design and C for the memory design. Alpha L and CL, if I want to find it out, the CL is nothing but the number of gates here, 915 to 10 raised to 6, multiplied by each of these gates will have the gate capacitance and then the diffusion capacitance. So we are accommodating both the gate capacitance and then the diffusion capacitance for a width, right? So this is per unit width of the transistor. So overall, this capacitance is nothing but 1.8 femtofarads per unit width of the transistors. right? So in this particular case, what we will have used is 950 into 10 raised to 6 gates, and 15 to 10 raised to 6 for the logic gates, and then the memory gates. Logic gates has, on an average has a width of 12 lambda. So 12 into lambda is 0.025 multiplied by the capacitances of 1.8 femtofarads, right? So that will give me CL as nothing but 27 nanofarads. So this is the overall capacitance I'm seeing for the logic gates. And similarly, the overall capacitance for the memory design will be 915 to 10 raised to 6 multiplied by, the width is 4 lambda here. So 4 multiplied by 0.025 multiplied by 1.8 femtofarads, it will give me 171 nanofarads. And so the P switching or the P average VDD will be nothing but the activity factor of the logic gate is 0.1. So 0.1 multiplied by 27 nanofarads plus the activity factor of the memory design is 0.02. So 0.02 multiplied by 171 nanofarads multiplied by 1 gigahertz multiplied by 1 square, which is nothing but the VDD square, will give me 6.12 watts. So remember that this chip design, it is still a very small chip design because it uses only the number of logic gates and then the memory, and it is only one particular die. There could be multiple such dies or stacked dies which are connected by the vias. So if I have that kind of a 3D stacked one, right? So the overall power, so the average power or the switching power or the dynamic power that has been delivered by the VDD turns out to be 6.12 watts and slightly more than that, right? So if I have a similar, one chip, you consume 6.12 watts, and if I have another chip and another chip and all of them are stacked together, right? So each one of this chip or each one of this die consumes 6.12 watts, then the overall design takes in more than 6 multiplied by 4, it turns out to be more than 24 watts, which is very, very high, right? So in that sense, what we need to do is, what we have understood now is how to estimate the power. But after estimating the power, we need to find some kind of a low power techniques so that the overall power, we get some power benefits, and then the overall power that has been delivered by the VDD tends to reduce, right?